Let me explain to you what we have done and what we will be doing. We were examining second order circuits. We found the mathematical model first. For an example, we examined that. That is the example that we have chosen. Here are parallel connected RLC circuit analysis. That is the state equation that we found. And then, once you found the state equations, then you're going to solve these equations. We said you could use the mathematical model, mathematical method that you have seen in differential equation course. How we use this mathematical tool, you're going to calculate homogeneous solution and find a particular solution, add them up, you get the general solution. In here we have done this. Homogeneous solution calculation here, and the particular solution calculation is here. Add them up, you get the general solution. So you see here our analysis is based on the parameters. All the element values are given as parameters. That means not numerical values. So here you are 1/r RC. So you are representing many number of circuits like that by giving different numerical values to these parameters. And what we said at the end on the general solution, we are going to calculate 4 k values, parameters here, and we said we've got 2 initial conditions. That's not enough, but we explained that we confined these state variables derivatives initial conditions by using the state equations we explained here. So it becomes now 4 known and 4 knowns and 4 unknowns. The knowns are the initial conditions of inductor and capacitor, which is given, and in the calculation these state variables derivatives initial conditions are also being calculated here. 4 knowns. Unknowns is that K11, K21, K12, K22. And then in the homogeneous solution we are calculating the characteristic root. Depending on the characteristic root type, either real or complex or the multiple roots, the format or the drawing of these functions are changing. Therefore we are examining these solutions for different characteristic root types. So for the real roots we have already examined here, and now we will be examining the complex roots. So that means we are going to choose, anyway I can say it on the open board, it is better. So for the complex case we are going to examine what happened. Here you are, this is the given circuit. That is the state equations for this given circuit, that is mathematical model. And these are the element values. These element values are not the same as we use for the real roots, because characteristic roots depends on the element parameters, that means RLC values. So when you change the RLC values, your characteristic root could be either real or complex or multiple. Real, we have done it and we changed the values in such a way, in this case the characteristic roots are going to be complex numbers, and we will be examining this case. So for these new element parameters, my differential equations numerical form is going to be this. What it is, if you replace that R and C with 20k ohm for R and C 0.125 microfarad, so this term becomes minus 4 times 10 to the power 2. So you're going to do similar things here. I have not done this. So we are in a position now, there is a circuit given to us with these elements and the initial conditions. These initial conditions are not the same that we use in the real route. This second order circuits, numerical state equations are those. Then what we are going to do, find the general solution for this circuit. To find the general solution, two steps that we are going to follow. For the first one is general solution is equal homogeneous solution plus particular solution. So start from the homogeneous solution now. Homogeneous solution, in order to find the homogeneous solution, we've got to calculate the characteristic roots. First we are going to find the characteristic equation and then characteristic root. How we are going to find it? Si minus a, determinant of it, is equal to 0. This is going to give us characteristic equation. So Si is this. So that means a unit matrix multiplied with this, with S. Unit matrix is the one on diagonal has got one values only. It is a unit matrix. Multiplied it with S, you get this. Minus, now this A is this. So minus 4 times 10 to the power 2 minus 8 times 10 to the power 6. 125, 0. From this, that minus S plus 4 times 10 to the power 2, 0, minus, so 0, this minus becomes plus, so that is 8, 10 to the power 6, and minus 125, and S, so determinant of this matrix. What is the determinant of this matrix? Multiplication of these two minus this, isn't it? S times S 4 10 to the power 2. So we could do directly the multiplication. We could do it. S square plus 4 times 10 to the power 2s. That minus, one more minus, makes it plus. 8 times 125 is 1000, isn't it? So this is 10 to the power 9. Equal to 0. From this, you're going to get two complex roots. One of them is this. $31,622, and the other root is minus 2. So the complex conjugate of this is going to be another root, isn't it? So you know it from mathematics. So in the previous one, our characteristic roots were real. Now they are complex. Since they are complex, our homogeneous solution for VCIL, let me write the H to represent homogeneous solution. It's going to be like that. K11, K121, e to the power minus 200 plus Ch9-4-2-1 622 T plus K12 K22 complex conjugate of this e to the power minus 200 minus J31 622 T. That is the homogeneous solution. What about the particular solution? You remember, since our independent voltage source is DC, particular solution is going to be DC as well. When it is DC, we can use the definition relation and we can calculate the particular solution from the circuit. You could do it in mathematics in different way, but let's do it here for this special case by using the circuit theory. So VL is L times di over dt. What does this mean? Particular solution is going to be constant since the source is constant. Derivative of it is 0. That means VL equal to 0. That means short circuit. So inductor is going to be short circuit, and when you come to capacitor, dVc over dt, since the Vc is constant, derivative of it is 0, so from this you can get that IC equal to 0. That's open circuit. So when it is open circuit, let me transfer that information to our circuit. That's going to be open circuit, means take this out. This is going to be short circuit. It's going to be like that, short circuit. Voltage is 0. So since these R and L elements are connected in parallel, so resistor voltage is also 0. By definition, VRI, resistor's current is also 0, so that's going to be open circuit as well. So in this case, this open, so this independent source current passed through this inductor. Inductor current, that is particular solution, is going to be equal to that source. So from that conclusion, IL particular is equal to this source. Kirchhoff current law, if you write it for this node, is going to be this equals 1 amp. So let's come to capacitor voltage. Capacitor voltage is going to be 0. So particular solution for the capacitor is going to be 0. Why is that? Because we already know that inductor voltage is 0 since they are connected in parallel. So that's going to be 0 as well. So VC particular is equal to 0. So if you transfer it to here now, make it general solution, put here the particular solution. So particular solution for the capacitor, it was 0. I put 0 here. For the inductor, it's going to be 1 here. So that is now general solution I found. This part is homogeneous part, and this part is particular solution. Add them up, find the general solution. So we finished now, except these parameters. So how we are going to calculate these parameters? We already said that we are going to use initial conditions. So 2 of the initial conditions are given here. And then we said we are going to calculate initial conditions for the state variables derivatives initial conditions. So that means in here, this is our state equation. If we replace with t equal to 0, so this is going to be derivatives initial conditions that I am looking for. And this, when t equal to 0 on the right hand side, that is going to be initial condition of the capacitor, which is 0. So that is 0. And this is when you replace this, there is a t here, when you replace with t, so it's going to be this, isn't it? So this value is minus 0.5, maybe write it this way, is so 500 milliamp means minus 0.5 amp, isn't it? So if you do the calculation, so we put the numerical values here, so right hand side numerical values, if you calculate this, you're going to end up for this one, initial condition. Let me write it here, dVc dt when t equal to 0. I'm going to look at that value from the Prezi, because I don't want to repeat these calculations here. Where is that? Here you are. 12 10 to the power 6 is the initial condition of the capacitor voltage derivative, and ILT equal to 0 is equal to 0. So 12 10 to the power 6, if I go back, 12 10 to the power 6 DIL 0 dt is equal to 0. So these are the derivatives initial conditions, and these are the VC equals 0 from here, and IL0 is minus 500 milliamp. So I've got 4 initial conditions and 4 K values that to be calculated. Don't worry that you're going to, whether you're going to calculate 4 unknowns, 4 equations. It's going to be just 2 equations, 2 unknowns. How it's going to be, if you consider the first equation now here, that is VCT K11 e to the power minus 200 plus J 31 6 22 T plus K12 e to the power minus 200 minus J 31 6 22 T. I am just repeating what it is. In a particular solution is 0, I don't write that. So this is our VCT. So in this VCT, there are 2 things to be calculated. So if you replace T with 0, this is going to be this initial condition, isn't it? So 0, and T equal to 0, e to the power 0 is going to be 1, so this equal K11 from the first one. The second one is that K12 is going to come in. So that's the first equation that we found. And then the second equation, how we are going to find it? Find the derivative of this function. So derivative of this function, dVc over dt is equal K11 minus 200 plus J 31 622 e to the power minus J 31 622 T. So that is the derivative of this first term here. The second term derivative is K12 minus 200 minus J 31 622 e to the power minus 200 minus J 31 622 T. That's the derivative. So when you replace t with 0, left hand side, right hand side, so that is the one that we have calculated here. Where it is then? Here are. Here are. So that means 12 10 to the power 6 is equal. So that's going to be e to the power e to the 0. So that is going to be 1. So K11 minus 2 plus J31 622. And then this term is going to be when you replace t with 0. So K12 2 minus 200 minus J31 622. So that's the first equation, that's the second equation. From those two you can calculate the K11 and K12. You're going to end up with this value 380 times sine. I can write it there. VC general solution is equal 380 e to the power minus 200t and then sine 31622t. So what we have done here, we calculated that VCT. In this VCT we had only two unknowns. By using the derivative initial conditions and this itself initial condition, we calculated this K11 and K12 and we found this result. That means we used two unknowns and two knowns. That means we solved two equations, not four. But this is for only the VCT. You should repeat what we have done for VCT here for the ILT. You're going to find the ILT as well in the similar case. So let's do the interpretation of these results. Let's go back to Prezi again. Here you are. That's the Prezi. This is the VCT change here. VCT, the one that we already found. It is quite interesting. This you see here, this is the characteristic root. What happened is this. We know this our independent current source current is 1 amp. That means it is a constant and it is a DC. So you are applying a DC source signal to your circuit, and your circuit response gives you a sinusoidal function like that. So from a DC you introduce an AC, but quite critical that this AC signal disappears. Why it disappears? Because of e to the power minus 200t. That minus 200t, that means this is exponentially decreasing functions. So it is this function. So it damps this signal and it goes to 0 after a while. This is 12 milliseconds. Maybe in 20 milliseconds this is going to disappear. So this term is going to disappear. That sinusoidal signal is disappear. What we are going to see is just 0. That 0 is the particular solution of that VCT. You remember particular solution of VCT was 0. So you see that. Interesting thing is, we are observing the characteristic roots real and imaginary part in our solution. That is, that 200 minus 200 is the real part of our characteristic root, and this 31,622 is the imaginary part of our characteristic root. So when the complex root, if the characteristic root is complex, this complex number's real part, as seen here, and imaginary part is the angular frequency of our signal, of our sinusoidal signal. So that is interesting, of course. So if you do it for the inductor, so you're going to end up a function like that. In this function, you see there is a particular solution here. You can check this particular solution. After 20 milliseconds, this transient solution is going to disappear, which is the homogeneous part of our general solution. And we will be observing only the particular solution. Particular solution for the inductor was equal to 1. So it's going to be 1 here, what we observe after 20 milliseconds, because it is 12 here, 20 is going to be somewhere here, so that is going to disappear, that means. Okay, another thing that we could check, if you see that this is the inductor current must be start from the initial condition of the inductor, which is minus 500. So here you are, minus 500, it starts from that point. There is no instantaneous change in the inductor current, isn't it? Before that, inductor current was equal to this. So from that point, it goes up. There is no any jump or any instantaneous change. So that is interesting in terms of if your characteristic root is complex, then you're going to observe a sinusoidal signal in your system. This sinusoidal signal is not related with your source function. Source function is DC, but you are observing a sinusoidal signal. So there are some other interpretations, of course, that you could do. If, for example, this real part is equal to 0, only the imaginary part, so you're going to get a sinusoidal signal from a DC source driven circuit. That is quite interesting. So that is the end of this video then, so we can stop it.